In this video we'll talk about Dijkstra's algorithm for solving the shortest path problem. So first let's talk about the major assumptions that we make in the shortest path problem that we are solving. First of all, we are dealing with a directed network. Every arc has a direction, and then there are weights associated with the arcs, typically represented the distance, the time of travel, or the cost. And one major assumption that we have for Dijkstra's algorithm is that the arc weights are all non-negative. Of course, naturally, with the parameters that I mentioned, like the cost, the time, and so on, it's natural to assume that the weights are non-negative, but in general, it doesn't have to be the case. And in particular, in some applications, let's say you may be getting paid if you travel through a certain road. Alright, so let's say if you travel through a certain link, you may pick up certain profit, and then in this case, the cost of this trip over this arc can be considered negative. So the Dijkstra's algorithm cannot be applied to problems where the arc costs are negative. And we will actually see why when we do the steps of the Dijkstra's algorithm. As you may recall, there are several different variants of the shortest path problems. For example, you could have looked for the shortest path between a particular pair of nodes. Then there is a variation where you look for shortest path between any two nodes in the network. The version that we are considering here will be the single source shortest path problem, where we have a single source node, node 1, and we are looking for the shortest path from node 1 to all the other nodes in the network. So now we are ready to describe the idea of the Dijkstra's algorithm. So Dijkstra's algorithm belongs to the category of what we call the label setting algorithms. Why is it called this way? Because there are certain labels associated with every node that we are going to set during the execution of the algorithm. In particular, there are two types of labels associated with every node. The first label is the distance label, and the second one is the predecessor label. The distance label indicates the length of the path that you currently have from node 1 to your node. And naturally, the distance label for node 1, which is the source node, is 0 because you don't have to travel any distance from node 1 to node 1. And then the predecessor for node 1 needs to be set to some numerical value, so we just set it to 0. There is no node 0 from which you arrived to 1, but we just need to specify something for this label. So to initialize, we set the distance label of node 1 to 0 and the predecessor label for node 1 to 0 as well. And we set all the remaining distance labels to infinity. And we don't have anything for the predecessor labels because we haven't started the steps of the algorithm yet, so we haven't reached any of these nodes. There is no predecessor. But generally, the predecessor will be the previous node from which you arrived to this node that gives you the distance from the node 1 that you have in the distance label here. Alright, so here we have all these distance labels summarized in the vector d, and then we also have the list of what we call the active nodes. The active nodes would be the nodes that you already reached and which can still be used to improve the distance labels of other nodes in the network. So to start with, we have the distance of 0 for node 1, the distance of infinity for all the remaining nodes because we haven't reached them yet from node 1, and then the list of active nodes consists of node 1 in which we start our journey. Now this completes the initialization stage and we are ready to start the steps of the Dijkstra's algorithm. During the iterations of the Dijkstra's algorithm, our goal is to label these nodes with their optimal values for the distance and the predecessor. So in the beginning, labels are temporary, but once we determine that a certain distance label cannot be further improved, what we do, we make that label permanent and we stop the algorithm whenever all the labels are made permanent. Alright, so how do we make the label permanent? For that, we go over the vector of the distance labels and we pick the smallest distance label that have not yet been made permanent. Alright, so in the beginning all the labels are temporary, and we start by making the label for node 1 permanent because the distance of 0 cannot be improved, right? So we make this label permanent and we proceed to the next part of the Dijkstra's iteration, which is exploration or distance updates. So we are going to what we call explore this node 1, and this is done by trying to look at its out neighbors and trying to see if you can update the labels for the neighbors by going there from the node that we are exploring. So in the beginning we are exploring node 1, so we try every outgoing arc from node 1 and see if we can use that arc to improve the distance label of its neighbors. Alright, so going from 1 to 2, we can do it in 2 units of distance, therefore we can update the distance label for node 2 from infinity to 2, and this distance is achieved by using 1 as the predecessor. Alright, so similarly, if I look at the other arc coming out of 1, then I can update the distance label for node 3 to 4, and the predecessor with which we achieve this distance label is 1. So the fact that we now reached nodes 2 and nodes 3 means that we need to add them to the list of active nodes, because they've been reached already and their labels have not been fixed yet. And the fact that we already explored node 1, because we tried all the outgoing arcs and we updated all the labels we could with node 1, means that node 1 has been explored already and we need to remove it from the list. So we are going to update the list, we'll remove node 1 from there, but we will add nodes 2 and 3. And then we will proceed to the next step. So let me go over this same step again by using the color coding that we have in the slides. So by fixing the label for node 1, we color it in red. Okay, so the red will be used for the nodes for which we already made the label permanent. We will also use star to indicate this permanent label in the D vector. Alright. And then once we made the node permanent, once we colored it in red, what we are going to do, we are going to look at all the outgoing arcs that we can use to update other labels. So we're going to mark these arcs with green color, and then the nodes that we reach for the first time by doing this are going to be marked in green also. So green labels for the nodes will represent the active nodes that will be added to the list. So you see we added them to the list as soon as we colored them in green. We updated their labels for the distance and for the predecessor. Alright, so and now we updated the distance labels also in this vector containing all the distance labels. So now we see that we have one permanent label and then the rest are still temporary, right? And we are ready to proceed now to the next iteration of the Dijkstra's algorithm. So we start the iteration again with the node selection process. We go to the vector D and we select the smallest distance label among those that have not been yet made permanent. This label obviously is 2 here, and the distance label of 2 corresponds to the node 2, so we make this label permanent, and therefore we are going to color this node in the red color. Alright, and this arc between the 2 red nodes is also marked in red because this arc is going to be a part of our optimal solution. Look, the predecessor for 2 is 1, and to reach the optimal distance label for 2 we need to come there from 1, so therefore this arc must be a part of the optimal solution, and once it is a part of the optimal solution, we mark it in red also. Alright, so right now we already have a piece of the optimal solution. And by the way, why can we claim that this distance label is going to be optimal for node 2? Is because the only way I can improve this distance label is by updating it by exploring some other node, right? So, but because all other nodes that have not yet been explored have higher labels, there is no way I'm going to make this label smaller unless I would have negative arc weights, right? So, and this is why this assumption that there are no negative arc weights is crucial for this algorithm, because it allows us to make this label permanent and claim that this label is optimal for this particular node. If we had negative arc weights, this would not have been possible, and this algorithm is not applicable for that situation. So there are other algorithms though that we call label correcting algorithms that are typically used for cases like that when we have the negative arc weights. Okay. All right, so let's proceed to exploring this node 2 now. So we made this label permanent. We will look at all the outgoing arcs from this node to all the nodes that have not yet been made permanent. And such arcs are 2, 3, 2, 4, and 2, 5. All right. So, and the node 3 is already on the list of active nodes, but when we explore node 2, we will have to add nodes 4 and 5 also to the list of the active nodes. And you see, we add these nodes by marking them in green here, and we put them in the list. So now 3, 4, and 5 are active nodes. And once we explored node 2, we remove it from the list of active nodes, right? So when we explore node 2, we update the corresponding labels. So when we go from 2 to 3, the way we try to update the label, we look at the distance label for node 2, which is 2, which means that we reach this label by the distance of 2 from node 1, right? And then if we go from 2 to 3, we need to add the weight of this arc in order to update the distance in which we reach node 3 by coming from node 2. So we can see that 2 plus 1 is 3, which is better than 4 that we had before here. So therefore we update the distance label to 3, and we update the predecessor label to 2 because we reached this node with the distance of 3 from node 1 by coming from node 2, not from node 1 directly, right? So the predecessor is node 2 now. Alright, so then because nodes 4 and 5 had infinite distance labels before, obviously we will update these labels to 6 and 4 respectively. Why 6 and 4? Because the distance label for node 2 is 2, and then when we travel from 2 to 4, this adds the distance of 4. So the total distance from 1 to 4 with the predecessor being node 2 is going to be equal to 6, right? So similarly here we'll have the distance of 2 plus 2, which is 4, and again the predecessor for node 5 is 2 right now. Okay, this completes the second iteration, and you see at every iteration exactly one node becomes red. So we fix the label for one of the nodes and make it permanent. Therefore, the total number of iterations that we'll have to execute will be exactly as many as there are nodes in the network. So if we have n nodes, then the number of steps will be n. Okay. All right. So now we start the third iteration. So now we have two permanent labels, and we look at our distance vector and pick the smallest label that is not permanent yet. And this would be the label of 3 that corresponds to the third node. So we'll make the label for 3 permanent now, and we are going to explore node 3 next. All right. So node 3 now is colored in red, and because the predecessor for this node was 2, the corresponding arc through which we came to this node and achieved the minimum distance is now marked in red. The next part of the third iteration would be distance update. So now we are going to explore this node 3 that we just made permanent. And for that we again are looking at the outgoing arcs. There is only one, right? So we are going to try to update the label for node 5 by coming from node 3. And the distance of going from 1 to 5 by means of 3 would be 3 plus 3, which is 6, which is greater than 4. Therefore there will be no update, right? So we are going to explore this node, but there is no update to the distance label for 5. And we cross node 3 out of the list of the active nodes because we cannot use it to further improve any of the labels. We already used all the information about the outgoing arcs from this node, right? So we proceed to the next iteration. So the next iteration again starts by node selection. Node selection would be, again, we are looking at the smallest label that has not been yet made permanent, and this would be the label of 4, which corresponds to node 5. So we are going to make this label permanent next. Alright, so this node is going to be colored in red. This arc is going to be colored in red because this is our predecessor for node 5 in the optimal solution, as we can see from here. And then we are going to explore this node 5 by looking at the outgoing arcs from 5 to 4 and from 5 to 6, right? So if we go from 5 to 4, let's see if it helps us to improve the label for node 4. The current label for node 4 is 6. If you were coming to node 4 from 5, the best we could do would be 4 plus 3, which is 7, which is greater than 6. Therefore, there will be no update to the distance label or the predecessor label for node 4.
Am I upset? No, I am not. A little, but...
But when we go from 5 to 6, here obviously we'll have the update because this is the first time we reach node 6, and the first time we reach it, we change the label from infinity to whatever we get by reaching it, right? And the new label for node 6 is going to be 4 plus 2, which is 6. Alright. So as we said, at the node selection stage, the node 5 was colored in red and the corresponding arc between the predecessor and node 5 was colored in red. And then we explored the node 5 by looking at the arcs 5, 4 and 5, 6. We don't update the label for node 4 because we don't have improvement, but we do update the label for node 6. So now the only remaining active nodes would be node 4 and node 6. Both of these nodes have the distance label of 6, so we can just pick any of them to be fixed at the next iteration. So let's pick the node 4 and we make it permanent, and obviously we cannot update any more labels because the only remaining node that has not been yet fixed is node 6 and it has the same distance label. Nevertheless, we'll proceed according to the algorithm and we will explore node 4 by looking at the arc 4, 6. Obviously there will be no improvement, yet we still color it in green. And then finally at the last step, step number 6, there is only one active node remaining, and obviously the distance label of this node is the only distance label that has not been fixed yet. So it's the smallest one among unfixed, right, of which there is only one. Therefore, we fix the label for this node, make it permanent, and once we made the label for node 6 permanent, we cross it out of the list of the active nodes, and at this point there are no active nodes, and we terminate. And let's see what we get as the result. We obtain what we call the shortest path tree. that can be used to determine the optimal path from node 1 to all the remaining nodes. And there is exactly one path between node 1 and every other node in the network. So these tree of shortest paths can be used to determine all the optimal paths from node 1 to all the remaining nodes. For example, if I take node 5, let's say, and I want to determine the optimal path from node 1 to node 5, what I do, I go from 5 to the predecessor, which is 2, so I kind of trace back the way we reached node 5 from node 1, and then the predecessor for node 2 would be node 1, so the shortest path between 1 and 5 would be through the node 2, so you would have 1, 2, 5, and to determine the length of this optimal path we need to sum up the length of arcs along this path, which is 2 plus 2 gives you 4. And this way we can determine an optimal path from 1 to all the remaining nodes in the network.
Yep, take 2 lefts, swim straight, and you'll hit it.
Oh, that's a lot of directions.
So this slide provides the summary of Dijkstra's algorithm, so let's recall what we have done in our example.
You don't remember what we were talking about?
So we started with initialization, where we labeled all the nodes with temporary labels representing the currently found distance to the node from the root node 1. And initially node 1 is given the label of 0, and the rest of the nodes are assigned the distance label of infinity because they were not reached yet. And then the iteration consists of 2 parts. In the first part we have the node selection. This is when we fix one of the labels that corresponds to the minimum distance label, and it is made permanent, right? And then after that we proceed to the distance update, or what we call the exploration of this node that we just fixed. We look at all the outgoing arcs from the new permanent node that lead you to the nodes that have not yet been made permanent, and update the distance labels accordingly whenever we can. And we keep going until we make all the distance labels permanent, at which point we terminate and we will obtain the tree of shortest paths as our output.
Just keep swimming, just keep swimming,